we already take. So let's go to notes. So as per clause, we have digit, as you seen in IS-456. Now the AST provided is pi by 4 into 10 square by 190 into 1000, that is equals to 413.367 or 413.37 mm square. This is the provided AST. As we have reduced the value of spacing, so provided steel area is increased. But there is a condition of minimum reinforcement and maximum reinforcement in clause number 26.5.1.1 under table 16a. AST minimum is 0.85 BD by Fy equals to 256 mm square. This is the minimum reinforcement has to be provided for this section, and AST maximum is equals to 0.04 B into capital D, that means overall depth, that is equals to 6000 mm square. So the value of AST provided is lies between this minimum and maximum, so hence this is okay. So we can provide 10 mm main reinforcement bar along shorter direction at the rate of 190 mm center to center. But let's check once the clause number 26.5.1.1 this condition. Okay, let's go to the code. So look here, AST by BD is equal to 0.85 by Fy. So from here a value of AST is equal to 0.85 BD by Fy. From that formula we have already calculated, and this is the minimum requirement of reinforcement, and the maximum requirement of reinforcement is the maximum area of tension reinforcement shall not exceed 0.04 BD. So as per our calculation, the area of steel provided lies between these two values. Let's go to notes. Now next step is distribution steel. For distribution steel, first of all we have to check out once clause number 26.5.2.1 of IS 456-2000. Let's go to code. Now check here clause number 26.5.2.1, minimum reinforcement. The mild steel reinforcement in either direction in slabs shall not be less than 0.15% of the total cross-sectional area. However, the value can be reduced to 0.12% when high strain deformed bars or welded wire fabric are used. In this case, we are using HYSD bars, so the second value 0.12% of cross-sectional area will be used. Let's go to notes and check. So see here, as per clause number 26.5.2.1, area of distribution steel, which is denoted by ASTD, is equals to 0.12 into BD by 100, that means 0.12% of cross-sectional area. So if we calculate 0.12 into 1000 into 125 by 100, that is equals to 150 mm square. So this is the area of distribution steel for this case. So we can use 8 mm dia bar. Here we are using 8 mm dia bars. So spacing is pi by 4 into 8 square by 150 into 1000, that is equals to 335 mm. So we can reduce the spacing, will be then 300 mm. So now maximum spacing is 5G or 450 mm as per clause number 26.3.3. So maximum value is this. So we have calculated, our calculated value is 300 mm. So therefore provide 8 mm dia bar at the rate of 300 mm center to center along longer span as distribution steel. So distribution steel part is also complete, but check once the clause number 26.3.3 about the spacing consideration conditions. So look here, clause number 26.3.3, maximum distance of tension bar. B2, the slabs, the horizontal distance between parallel reinforcement bars provided against shrinkage and temperature shall not be more than 5 times the effective depth of a solid slab or 450 mm, whichever is smaller. So our value is already less than that. We have provided the 300 mm spacing. So design is almost complete. Now we have to check. Our first check is deflection check. So from clause number 23.2.1 and figure 4 of IS 456, we know to find out modification factor, first of all we have to use the formula of Fs, which is just below figure number 4 of IS 456 2000. The formula is Fs is equals to 0.58 Fy into AST required by AST provided. So that is equals to 0.58 into Fy is 415 into AST required is 401.96 by AST provided is 413.37. We know these values. So that is equals to 234.056, or this is equals to 234 Newton per millimeter square. Now percentage of steel is AST provided by cross sectional area, that is B into D into 100. So that is equals to 0.33%. We know to find out modification factor from figure 4 of IS 456 2000, we have to know two values, that is Fs value and percentage of steel. From these two value we have to find out the value of modification factor. So let's go to figure 4. You can see in your screen figure 4 of IS 456 2000. So our Fs is 234 Newton per millimeter square, but there is no curved line of 234, but 234 is lies between 190 and 240. So we have to interpolate from these two lines. So first check for Fs 240 and percentage of steel 0.33, the value of modification factor is almost 1.5. You can check this value with the help of pencil or scale. And for Fs 190 we can assume the value of modification factor 1.9. So now we have these two values. From these values we have to find out the value of modification factor for Fs 234. So in your screen now you can see, so whatever our findings as per figure number 4 of IS 456 2000, for Fs 240 modification factor is 1.5 and for Fs 190 modification factor is 1.9. Therefore for Fs 234 modification factor is equals to 1.9 minus within bracket 1.9 minus 1.5 by 240 into 190 into 234 minus 190, that is equals to 1.9. So modification factor is 1.9. So effective depth is equal to span by base value into modification factor. Base value as per this clause is 20 for simply supported beam, as we see it earlier of this problem, early stage of this problem when we are considering the depth. So basic value is 20 multiplied by modification factor, whatever we find out, that is 1.9. so this is equals to 75. so required depth is 79 for deflection, to resist deflection, but our value which we have already considered is greater than that, that is 125 mm. so this is safe in deflection. Now check for shear. So to check shear, first of all we have to find the value of shear force, that is Vu, that is equals to WL by 2. This is written in clause number 40.2.1.1 of IS 456 2000 in page 72, but we already know that the value of shear force, to find out the value of shear force we have to use the formula WL by 2. so that is equals to WU, we have calculated the 13.875 into L is 3 by 2, that is equals to 20.81 kilonewton. Now nominal shear stress tau V is equals to V by BD. B is 20.81, which we have calculated just now, by B is 1000 into D is 125, that is equal to 0.16 MPa. Now value of tau C from table number 19. So from table number 19 we have to find out value of tau C. Okay, so let's go to table number 19. After that we will get back here. So we know a percentage of steel is 0.33. so let's go to the code. Now this is table number 19 of IS 456 2000, design shear strength of concrete tau C in Newton per millimeter square. The first column is 100 AST by BD, that means percentage of steel is 0.33 is in our case. There is no value for 0.33, but 0.33 is lies between 0.25 and 0.5. Our grade of concrete is 20, so 0.25, the design shear strength is 0.36 MPa or Newton per millimeter square, and 0.50 percentage our grade of concrete, when our grade of concrete is M20, the value of tau C is 0.48. so for percentage of steel 0.33 and grade of concrete M20, the value of tau C will be definitely lies between these two value 0.36 and 0.48. we have to find out that with interpolation method. Let's go to code, go to notes. So now look, the value of tau C from table number 19, as you see we have to interpolate. So value of tau C is 0.36 plus 0.48 minus 0.36 by this will be 0.5, not 0.75, mistakenly written here. You should when you note down this, you should write in your notebook. This will be not 0.75, this will be 0.5 minus 0.25 into 0.33 minus 0.25, that will be equals to 0.34 Newton per millimeter square or MPa. Now in case of slab we have to multiply a factor with tau C value to find out design shear strength. The K value we can get from clause number 40.2.1.1. so let's check this clause. Now look, clause number 40.2.1.1 of IS 456 2000, for overall depth. Now for solid slab, the design shear strength for concrete shall be tau C into K, where K has values given. So, these are the depth: 300 or more, 275, 250, 225, 200, 175 and 150 or less. Our overall depth value is 150, so the K value will be 1.3 for us. Let's check the calculation. So K tau C is equals to 1.3 into 0.34, that is equals to 0.44 Newton per millimeter square or megapascal. So tau C is less than K tau C, hence safe in shear. That means no shear design required for this case. So let's go to next step. So next step is development length check. For development length check, we know we have to go to clause number 26.2.3.3, page 44. From this clause, we will get the formula m by v plus L0 is greater than LD. So let's check the formula first from code. So here is the formula in page 44. M1 by V plus L0, that should be greater than LD. So for LD, in clause number 26.2.1, here is the formula for LD. We have seen the formula and detail in my previous lecture for single reinforced beam, which link is given in description box. You can check that there. The value of tau BD is given here in clause number 26.2.1.1. For grade of concrete M20, the value will be 1.2, and for deform bar it shall be increased by 60%, right? So let's go to notes and check it how these all are applied in design problem, in solving design problem. So here it is, dia into 0.87 Fy by 4 tau BD, that is equals to 10 into 0.87 into 415 by 4 into 1.2 into 1.6, that is 60% increased what we have read just now in IS code, right? So the value will be 470.11 mm, and L0 is either 125 mm or 12 into diameter, so that is 120 mm. So L0 is 125 mm. So m by v plus L0, that is equals to 16.93 into 10 to the power 6 by 20.81 into 10 cube plus 125, that is equals to 938.55, which is greater than LD. That means this is safe in development length. The next step is we have to write the design data. So all design calculation is done. We have already checked, we have completed the all checkings. So now time to write design data. After that we have to draw it. So capital D, that is overall depth, is 150 mm, small d effective depth is 125 mm. Main bar along shorter span is of 10 mm at the rate of 190 mm center to center. Distribution steel bar along longer span is of 8 mm dia at the rate of 300 mm center to center, and actual cutoff is 300 mm from the center of support. So let's check the drawing. This is the drawing. So main bar is 10 mm dia at the rate of 190 mm center to center, and distribution steel is 8 mm at the rate of 300 mm center to center. So here the solving of problem for one way slab is end. That's all for this lecture. Thank you.